Hello everyone and welcome to Sky Scholar. My name is Steve Crothers and today I will be exploring some aspects of the modern theory of white dwarf stars. This theory was derived primarily by Supernovae and Chandrasekhar, who received the Nobel Prize for this work in 1983. Chandrasekhar is viewed by many as the father of modern astrophysics. He played a critical role in the development of this discipline, having completed his graduate education at Cambridge under the guidance of both Ralph H. Fowler and Arthur Stanley Eddington. In fact, Chandrasekhar shared the 1983 Nobel Prize with Fowler. Still, well before receiving his Nobel Prize, Chandrasekhar was well connected within the physics community. He was the nephew of the famous Indian physicist Chandrasekhar Raman, who had won the Nobel Prize earlier in 1930. After completing his studies at Cambridge, Chandrasekhar eventually became a professor at the prestigious University of Chicago. He also served as the editor-in-chief of the Astrophysical Journal for nearly 20 years, from 1952 to 1971. His work was seldom questioned, and perhaps few would even dare to do so even today, given his position and his powerful descendants in astrophysics. It was Chandrasekhar who first argued, along with Eddington, that white dwarf stars are hyperdense objects, and such ideas have become widely accepted today. White dwarfs are often said to be 1,000,000 times denser than water, and Eddington claimed that they are 2,000 times denser than platinum. Recently, however, Dr. Pierre-Marie Robitaille has convincingly argued against the hyperdensity of white dwarfs on this channel, as we see in these 6 videos. It is clear that the observational evidence simply does not support the idea that white dwarfs are hyperdense. Today, I wish to build on Dr. Robitaille's work and bring to the forefront all theoretical problems with the modern theory of hyperdense white dwarf stars, in support of Dr. Robitaille's findings. My analysis was recently published in this article following peer review, and I invite everyone who is interested in the detailed physics to read the paper. The theory of white dwarfs is built upon 2 foundations, namely the ideal gas law and the laws of thermodynamics. As Dr. Robitaille previously highlighted in these videos, in any thermodynamic expression, it is necessary not only that the units on each side balance, but thermodynamic character must also balance. If the expression is not thermodynamically balanced, it is physically invalid, even if the units balance. Beyond the discussion of thermodynamic balance, in these videos, Dr. Robitaille and I have also covered the topic in detail in this paper. As a brief review, temperature is an intensive thermodynamic coordinate. Mathematically, it is a homogeneous function of degree 0. Mass is an extensive thermodynamic coordinate. Mathematically, it is a homogeneous function of degree 1. Pure numbers and physical constants have no thermodynamic character. Whenever temperature is given a non-intensive character in a thermodynamic equation, the relation must be false. Similarly, if mass is given a non-extensive character, then the expression is also false. Some thermodynamic coordinates are neither intensive nor extensive. Luminosity is an example, as one can learn by reading our paper. Now consider this mass expression for the gaseous envelope of a white dwarf. This expression, along with all others presented in this video, can be found in my paper, along with the citations of where these relations occur within the modern theory of white dwarfs. Here, capital M is the mass of the star, and capital R is its radius. The radius is homogeneous degree 1/3. Since temperature is intensive, so too is temperature to the power of 5 on 2, as exponents do not alter the effect of an intensive thermodynamic property within a thermodynamic expression. Given that temperature raised to an exponent remains intensive, then the right side is governed by R and M. Recall that constants and numbers make no contribution to thermodynamic character. R to the power of 4 divided by M is a homogeneous function of degree 1/3. This renders the right side a homogeneous function of degree 1/3. Yet the left side, being mass, is extensive. Consequently, this expression, which is central to the theory of white dwarf stars, stands in violation of the laws of thermodynamics and is therefore invalid. Next, consider this pressure equation for a white dwarf. Since temperature is intensive, so too is T to the power of 4.25. Luminosity L is homogeneous degree 2/3. So the quotient M on L is homogeneous degree 1/3. Pressure, however, is homogeneous degree 0 because it is intensive, in accord with the ideal gas law. This equation is therefore false. Now, as was covered in earlier videos on the subject, the quotient of 2 different extensive thermodynamic coordinates produces an intensive thermodynamic coordinate. Density is a simple example, being mass divided by volume. Given this fact, consider white dwarf density given by this equation. The right side is homogeneous degree 1/3 owing to the quotient of M over L. All other terms on the right side, except temperature, are pure numbers or physical constants, so they have no thermodynamic character. But density on the left must have a thermodynamic character of 0, so this density equation is also false. The temperature for the gaseous envelope of a white dwarf is given by this equation. Here capital R is the radius of the star's surface, and lowercase r is the location in the stellar envelope. Temperature on the left side must be intensive, but the right side is not intensive because the quotient mass over radius is homogeneous degree 2/3. This equation is therefore invalid. In his book on stellar structure, Chandrasekhar gives the envelope temperature by this equation. Capital H is the mass of a proton, and Z is a constant called the condensation. As a result, the only variables which govern thermodynamic character in this expression are T, M and R. Once again, temperature on the left side is a homogeneous function of degree 0, but the right side is a homogeneous function of degree 2/3 due to M over R. So this expression is also false. Note that this equation and the previous equation assign temperature to gravitational potential energy, but potential energy has no temperature. This is a major blunder by Chandrasekhar as to an elementary understanding of thermodynamics. It is argued in astrophysics that if the surface of a white dwarf is convective, then the envelope temperature is given by this equation. Here, gamma is a constant. This equation is invalid for the very same reasons as the previous two temperature equations. Next, the white dwarf luminosity is said to be given by this equation. Here, T sub C is the core temperature, G is the universal gravitational constant, and K sub 1 is a constant having the value 10 to the power of 13 in CGS units. Luminosity is homogeneous degree 2/3. The right side, however, is a homogeneous function of degree 1, as the mass m of the dwarf now governs thermodynamic character. Given that temperature is intensive and all other terms are either constants or numbers, as a result, once again, this equation is inadmissible. The astronomers advanced a relation between the core temperature of a white dwarf and what they call the effective temperature from the Stefan-Boltzmann law in this way. Here, lowercase t is called the guillotine factor, and lowercase g bar is the Gaunt factor, both constants. Capital Z is the number of protons in a nucleus. Capital M in the numerator is the dwarf's mass, and the subscripted m in the denominator is the mass of the Sun, rendering the dwarf mass in number of solar masses. The left side is therefore extensive, but the right side is homogeneous degree 2/3, so the equation is once again invalid. Furthermore, both sides of this equation are luminosities. The left side makes luminosity homogeneous degree 1, contrary to the Stefan-Boltzmann law on the right side, which is homogeneous degree 2/3. Consequently, the luminosity on the left side is invalid. Finally, the Chandrasekhar limit sets the maximum mass that a white dwarf can achieve. The proof that this limit is invalid is more involved and is given in my paper. So you see, nothing remains of the theory of white dwarfs advanced by Chandrasekhar when analysed in terms of simple thermodynamic requirements. It's little wonder that everything in astrophysics must undergo scrutiny and change. Well, that is all for today. If you enjoyed the video, promote the channel. Mention the video to your friends and to your local astronomy club. Support with a like or subscribe for more videos as we look more closely at the Sun, the stars and beyond. Comments are always welcome down below, and we'll see you soon in the next video.